Hey there, physical science students. This is Miss Ruark. We're in Unit 4. We're dealing with electricity. All right, so talk about electricity, we've got to talk about atoms. I know we haven't covered the chemistry part yet, but we'll get there. But we have to have atoms because there's a very special part of the atom that conducts electricity. So, in the parts of an atom, a neutral atom is anything that has an equal number of electrons and protons in it. So, question is, what in the world are electrons and protons? Well, we'll get there. All right, if you change the number of electrons, then you would end up with something called an ion. And an ion is an atom with a charge. Okay, if it's a positive ion, it has more protons than it does electrons. And if it's a negative ion, it has more electrons than there are protons. Okay, so below is a picture of a bare bones picture of an atom. Of course, this isn't what they look like, but it's there for representation's sake only. All right, so protons are these little green things. They're inside the nucleus, along with the neutrons, which are the red things. Protons have a positive charge, neutrons have no charge. Neutron neutral. All right. Electrons are on the outside. These things have a negative charge, and they just float around in this big space out here around it. We'll learn more about this when we get to the chemistry. Okay, so what creates a charge? Well, to create a charged atom, you have to either move out protons or you have to move out electrons. So the question is, well, which one moves? Well, if you go back and look at that picture of the atom that we just had there, which one's going to be easier to move? And if you said protons, you're wrong. Okay, those electrons are going to be easier to move. And the reason they're easier to move, whoops, let's go back, is because they are on the outside. Okay, the electrons are on the outside, so they're easier to take away. Think about it. Would it be easier if you were fully clothed and ready to go outside with your, it's cold out right now. So if you're fully clothed, you have, your pants, your shirt, you have a light jacket over top of that. Let's say it's snowing, so you decide to put on a heavier jacket and some other heavier clothes, like some snow clothes, because you're going to go skiing or something. I don't know. Would it be easier to take your underwear off or to take out that outside jacket? Well, if you said that outside jacket, you're right. If you said your underwear, then you need to, you're not in the right place. Okay, so electrons are going to be the ones to move. Why? Because they're on the outside. The protons are in the nucleus. You can't move them. They're bound. They're bound by a nuclear force that holds them there. All right, so electrons are not going to be created or destroyed. They're simply transferred from one material to the other. That's conservation of mass. Okay, because electrons are matter, because they have mass and they have volume. Well, guess what? Because electrons are used in charge, we call that conservation of charge as well. Okay, so conductors and insulators. Well, what's the difference between the two? Well, conductor, as you can see pointed here, is that wire. That's something that's going to allow the flow of electrons very easily. It's going to allow them to go, right? Party at my house. Not at my house, actually. Party at Tylen's house. Okay. This here would be the insulator. The insulator is the material that does not allow electrons to move easily. It still allows them to move. Think of the bouncer outside that really nice club, okay? The bouncer is only going to let certain people in. The rest of them can't go. So it's regulating or restricting the flow of those electrons. Okay, when you're dealing with electrical circuits and with electricity, you have to have a grounding wire. Okay, the grounding wire typically is going to be shoved into the ground, hence the grounding wire, and it allows charges to move freely from the substance to the ground. It keeps you from getting electrocuted, and it neutralizes the charge on the circuit. Yeah. All right, electric fields. Space around Earth and any other thing that has mass, so we have it as well, is filled with a gravitational field. We have gravitational fields and pulls on us. We just don't feel it because it's so small in comparison to the gravitational pull of the Earth. All right, well, around every electric charge, there's an electric field. And this electric field can have a positive charge or a negative charge. Positive field or a positive charge and a negative charge. If it has a positive charge, then the field, these arrows represent the field, is moving away from the charge. And if it has a negative charge, the field is going towards the charge. It's sucking in. Okay? So the direction of the field, like I just said, positive charge, the field points away from the charge. Negative, the field points towards the charge. So here's some examples. This one has two fields. Here's one, and here's the other. It kind of looks like a set of eyes. And if you'll notice, this has the charge going away from it. The charge is going away from it because it's pointing away. So this would be the positive charge. And this one has stuff going to it, so it has to be the negative one. Now, if you look on the other side here, there's two more eyeballs, right? Two more charges. Both of them have things moving completely away from them, so those are going to be what we would call positive charges. There's two positive charges next to each other. Notice how there's empty space here because they're repelling each other. They don't like each other. Okay, think stepbrothers trying to hug at the end. They end up high-fiving. All right, electrical potential energy. So the charge of energy is due to location in an electric field. If the charge was to be released, it would accelerate away from or towards the charge. Okay, depending on, if it's positive, it's going to go away. If it's negative, it's going to go towards. And the potential energy is going to be transformed to kinetic energy. Why? Because remember, potential energy is stored energy. As soon as it starts moving, it's now kinetic energy. Okay, and here's just a picture. Yeah, okay. All right, and I thought it would be really cool to give a little note out to those electricians because, electricians work, it's always fun. All right, I'll see you in class.